Okay, hey everyone, it's Professor Sebastian. Welcome back to our Calculus 3 class notes. We're now moving into section 14.7, and in this section we're going to be looking at extreme values and saddle points in this chapter 14 about partial derivatives. So what we're going to first talk about is what are some derivative tests for local extremes. So recall that for y equals f of x, for a function of a single variable like we talked about in Calc 1, we want to look for critical points. These are points where there's a horizontal tangent line, in other words, where f prime of x equals 0, or we also look for where the derivative doesn't exist. The second thing at these points is we look for local maxima, local minima, and points of inflection. Okay, so if the derivative is 0 or the derivative doesn't exist, we could have a maximum or a minimum. We also could have a point of inflection, which is where it changes concavity, and it's not a maximum or a minimum. Okay, now for z equals a function of x and y, we look for points where the surface has a horizontal tangent plane instead of a horizontal tangent line. In other words, where the two first partial derivatives, f sub x and f sub y, are both 0, or where one or both do not exist again. These are all still called critical points. Then local maxima are points where there is no greater value of f of xy nearby. That is, these are points AB such that f of AB is greater than or equal to f of xy for all domain points xy in an open disk centered at AB. So you can kind of visualize that better with my drawing down here. So these are local maxima. You can imagine like a mountaintop. You're standing on the mountaintop. So there's some small open disk, and every point, no matter which direction you go, you'd be going downwards. So those are local maxima. Similarly, local minima are points where there's no smaller value of f of x nearby. That is, these are points AB such that f of AB is less than or equal to f of xy for all domain points in an open disk centered at AB again. So this is a picture of a local minimum, where if I were to walk out of the bottom of this valley, I'd have to go up no matter which direction I went. So in this open disk, everything there from at this point AB has to go up. Okay, so as an example, this is just I just wanted to do a show me example where I graph some different functions using GeoGebra, just to kind of give you an idea of how these things could look. So let's consider the function z equals cosine of x times cosine of y e to the minus square root x squared plus y squared. So we're not learning how to find the maximum and minimum yet, but there is a maximum value of 1. You can see that right here. And a minimum value of about negative 0.67 over the square domain x less than or equal to 3 pi over 2, y less than absolute value of y less than or equal to 3 pi over 2. Okay, so you can see these shaded areas GeoGebra. That means that those are a little bit below the xy plane, and all of those go to minus 0.67. Okay, so now if we just consider z equals cosine of x cosine of y, I look at it in the typical way we look at it, looking down in the first octant at it, or I rotate it up a little bit after forming it. You can see there are multiple maximum minimum values, local maxima and minima. They're all plus or minus 1, which makes sense. We know cosine and x and y, they both go between minus 1 and 1, so their local maxima and minima should be at minus 1 and 1. Another interesting surface to visualize is often referred to as what's called the roof surface, this guy right here. So it's z equals 1/2 times a quantity, absolute value of the absolute value of x minus the absolute value of y, and then minus absolute value of x minus absolute value of y. So it looks like a roof. This function surface has a maximum value of 0 and a minimum value of minus a on the square domain region of absolute value of x less than or equal to a, absolute value of y less than or equal to a. Okay, so between 0 and a on the x-axis, 0 and a on the y-axis. And you can see that we have a minimum value of minus a. You can't really see it that good, but you can see the maximum is 0. Okay, so that's just a show me example, just to show you what kind of things we're going to be looking for.